Okay, in this lecture, we're going to look at how you might implement something. You see like this diagram here, and you might think, what is it? It kind of looks like maybe the neurons in the brain or something like that. But what it actually is a diagram of sort of connectivity in the internet at some, point in history a number of years back. And as you might imagine, this wasn't really drawn by hand, right? This was drawn by a computer, and somehow all these interconnections in this intricate web of network connections had to be represented in an abstract data type. And so we're going to look at different ways to represent things in abstract data types, and in particular we're going to look at a lot at linked data structures today. And as a reminder, so what is an abstract data type? An ADT? It's a collection of data and operations on the data in that collection, versus when we talk about a data structure, we're actually looking at how that ADT is implemented. And this is a choice. There are more than one way to skin a cat here. And the different choices you make have different maybe realities and how much time it's going to take to add something and remove something, or to how much memory it's going to take up, and so on. And there are a variety of different choices, and one possible choice in the stack array activity, you looked at implementing a stack using a fixed array. This time we're going to look at, well, what if we make that dynamically sized so we can actually get the API we want for the stack ADT. And then this time we're also going to look at a linked data structure. This is something we haven't seen before, but it's a very, very common thing to do in data structures. It allows you to hook things together sort of in any way you can imagine. It allows you to build lists or stacks or queues or graphs like that graph of the internet I just showed you, or things that branch, that branch in 2 ways or 3 ways or 5 ways or whatever you want. They're very flexible data structure. Let's revisit our friend, the first in, first out stack ADT, and it has to support being able to push things and pop things. And last time, or in the activity, we did a stack of strings array. And remember, to do this, to simplify our life, we kind of cheated a bit. We really wanted a ADT that could store as much data as we wanted, but our ADT requires the user to a priori decide how many things may go into that stack, which may be a hard thing to decide. And if they decide it's too small and you try to put too much data in, it's going to break. All right, but the advantage is it's very easy to implement. Just using you just create one array in that constructor and you're good to go. And here is the solution to that stack of strings array. And remember, we created our array up here of fixed size, and we had this little last index that tells us where to put the next thing, and we can check if we've hit that limit. And we really don't like this part. Really, a stack ADT should be able to just push and push, subject to the memory constraints of the computer. So we don't really like having this first runtime exception. It really shouldn't have that. However, this stack is empty runtime exception, well, that is a little bit unavoidable. If somebody tries to pop an empty stack, well, you've got to decide what to do. And really that person probably should have checked is empty before they called. And it's unclear. I mean, this is one choice, is to throw an exception, or you could return some kind of flag value or something that indicates you didn't get a real result back or something like that. Let's put this fixed array stack class against all of Moby Dick. Okay, so in the file mobydick.txt, I have all the text of the novel, and what we want to do is reverse all the words in Moby Dick, and the last word is a go, and then here's some of the others. So the punctuation makes it a little strange, but that's the idea. What if we wanted to reverse the entire book? All right, and here's how that might go using our existing stack of strings array ADT that uses the fixed array data structure. And we're going to have to decide how big to make that. And let's say we're going to make it 100,000. Okay. And what happens is we're going to execute this line, instantiate that stack of strings array. And when that constructor fires up, first we've got the items instance variable, and it's not, it's null. It's a reference type. Okay, so its default value is null, and last default value is 0. Once we execute the constructor, items gets instantiated, and we create 100,000 slots from 0 up to 99999, and all those have the potential to store a string, and then that last thing is equal to 0. We signed it equal to 0, but it was already in the default value of an integer is already 0. And recall, okay, the default value for a string, we've created essentially slots for all these string objects, but we haven't actually created, we haven't instantiated any of these string reference objects. So actually all the slots in the array initially start with null. All right, and as we go through this loop in the main program, it's going to push, it's going to read something in and push it in the stack, and then that last number is going to get incremented in the push method. And here is various words getting pushed into the stack, and all goes well until and all is still going well. We pushed, turns out the 100,000th word in Moby Dick is sudden, and that gets pushed, and that's fine. But we push something else, and that's it, or we get a runtime exception. Here's our thrown runtime exception with the message stack is full, and then that's it. We're never going to see the reverse version of Moby Dick, not at least with a stack that only has 100,000 potential slots in it. Here's a modified version of reverse words, and so all I've done is make the size of the stack configurable by the first command line argument. And I'll just here is Moby Dick. It has 209,341 words. So WC is a Unix utility that counts words in a file. And then I also have this much bigger file. This is 200,000 sentences from Wikipedia. And you can see here is kind of their size on disk and so on. Because I ran this program first, I know exactly how many words I need in my stack. And so now when I call it, I can actually call it with the proper amount. And this thing will get completely full, but I don't try and push. If I try to push one more word, it would explode. But I stay, I can, restrain myself and only push 209,341 words, and it works. And this stats thing just measures. So I create this object here, and then I print it out, and it prints out how much time elapsed in seconds, as well as the approximate amount of memory that was used by the program. So that's the second number you see here. And here we can load Wikipedia, and in that file it has 3.8 million words in it. Okay, that one took a little longer to parse and took a lot more memory as well. That's good, but we had to sort of have this knowledge before we ran the program. Okay, which makes us a little uncomfortable. As the designer of this implementation of the ADT, we don't really want to rely on our users counting the number of words beforehand and calling us with the appropriate constructor argument. This brings us to the topic of dynamic arrays. It's, as the name says, it's an array that can size itself. This is just like the array list we've seen in Java before. One way to do this is just to use, you can still use the fixed array just like we did in the stack of strings array example, but it needs to do something when it runs out of space. It needs to make a bigger array and then copy the new data into the array, and then switch things over to the new array. So you can imagine starting out with only 2 slots. Okay, we add a 2, and then we add a 7. Okay, but then we add the 1. Well, to get the 1 in there, what do we have to do? Well, we had to expand. We could say, for example, double the number of slots, and then copy 2, 7, 1 in there, and then we add the 3, and then when we try to add the 8, we run out of room again. So this time we add 4 additional slots, and then so on. We've got sort of a logical capacity, and then, or a logical size, and then a total capacity. Capacity is how much how many total slots we could use, and then logical size is how many things are actually occupied in the array. There's some different choices about how you expand it. All right, and I'm going to show you the realities of what happens if you do either of these. And one would be, well, somebody wants to add a 1. Well, I could just make it 1 bigger. That would give me just enough space to put the 1 in, and then if somebody adds a 3, I'll make it 1 bigger, and so on. That's not what this diagram is doing. This diagram is doubling the current size. Okay, hopefully, avoiding having to do it, for a longer period of time after the doubling. Here is that first solution, which is just making the array 1 bigger. And we've got a more sophisticated, okay, the setup is the same, and I've got some constant here in its size, and this just says how many things I'm going to start out with. So I just chose 16. Now, instead of just throwing, before what we would do if we run out of capacity, if last equals items.length, we would just throw an exception. Now we're trying to do something smarter. Instead of throwing an exception, we'll create a new array. Okay, it turns out you can't just like tack on to the existing array. We have to create a whole new one that is the size of the old one, and let's add 1 to it. And then we can copy in all the old items. Okay, all right, and then set the instance variable equal to this local variable bigger. So essentially what we're doing is we're kind of taking, we got this one array, then we make a new one that's a local variable, and then we switch the reference over. And so once we do the switch, items, the instance variable, is now equal to this array that's 1 bigger, and the old items is just no longer referenced and will be garbage collected by the JVM. Once we've copied everything over, then we have the extra slot we needed. We can put the data into that slot and increment by 1. Okay, that's increasing by 1, and it is good because it uses the least amount of memory, but it's bad because it takes forever. Okay, I don't recommend you implement it like this. And this is an example of how you can create a simple algorithm that takes enormous amounts of time. And here is using reverse words 3, and the nice thing now is I don't have to specify that command line argument. I can run on any size file and it will work, but it may take a very long time. So you can see here on the Wikipedia data, it's taking I don't know, 7 some hours to reverse all the sentences and stuff in that file. Versus here's the result from last time. If we tell it exactly the right amount, all right, it took 3.6 seconds. Okay, that's a big difference. And that is all the overhead associated with this. Every time we needed, once we got beyond that first 16, every single time we added a new word, we had to copy that whole array over, and that's very expensive. Okay. Here's a more sensible implementation. This is a array doubling strategy. Instead of doing that increase by 1, well, let's increase it, whatever I used to be, I'll double it. And then I'll copy the data in, and the rest just proceeds the same. All right, and look at the difference that makes. Okay, versus the last one where it took almost 25,000 seconds for that Wikipedia. Now it's back down to 3.6 seconds. All right, a massive difference. All right, and it's on the order of even this other solution where it actually knew exactly how big to make it. Right? It's really not that expensive to do this doubling, because that's kind of the power of doubling something, right? You at the very beginning, yeah, okay, we double from 16 to 32, and then 32 to 64, and then 128, and then 256. But every time we double, it gets bigger and bigger, and the frequency we have to double by the end is very infrequent. Now, you might be thinking, well, why are we doing all this? We could just put it in an array list, and that's true. We could, instead of implementing a stack using our own doubling array, we could create a Java array list. And it turns out a Java array list is doing something similar to the doubling array solution. Though if you read the Java docs, so here's a section from the Java docs, it's saying the exact specifics aren't specified, other than the important bit you're getting, adding an element has constant amortized time cost. And what that is code word for we're doing something like doubling. Okay, we're not doing something silly like only increasing by 1 or only increasing by 10. By doubling it every time, you get this inexpensive constant behavior. Like it's really not that expensive to add is the bottom line. And we can compare this particular stack ADT using array list versus my array doubling, and you can see, okay, maybe, it's not, I kind of was faster here and they were, kind of faster on Moby Dick, but it's pretty much the same. Okay. And so now you've actually seen, if you're wondering what kind of magic was going on in the Java array list, that's essentially the magic is this code I showed you here. It's not really that complicated. You just double the array, copy the data, and then you have twice as much space to put stuff. The data types we've been looking at so far, like these arrays, are sequential. Every object follows another object, and what we're doing is when we allocate an array, we've got a single big block of memory, and all those things are consecutive in that block of memory. And what's nice about this is you can get straight to what you want. All right, by using an index into the array, use a square bracket 105, you can go directly to that memory that contains that 105th element. All right, that's the advantage. The disadvantage is it's fixed in size. Okay, we saw how to double it, but the only way to double it is to take that one block that was, size n and make a new block that's like 2n and copy everything into it. But you still have to operate with these things that are in sequential blocks. This is different than a linked data structure, and in a linked data structure what we have is objects that link to another object, okay, or perhaps several objects. All right, we're going to look at a simple case today where each object links to a single other object, and this is another way to get a dynamically sized data type. And it's very flexible. It's much more flexible than sort of a doubling array. You can create any kind of crazy, you can create graph structures, you can create trees, you can do all kinds of different things with a linked data structure that are pretty difficult to do with an array. Here is a comparison of a sequential and a linked structure. A sequential structure like an array might contain a bunch of slots. How many do I have here? 10. That can store 10 different strings, and the cat sat are the first 3 things in there. All right, at memory address C0 and C1 and C2. Okay, and we've got strings in here. A link structure, okay, kind of the spirit of a link structure is that's not how it's going to work. We're actually going to have things linked. Okay, we're going to have 2 things. Okay, first we're going to have our payload, sort of, okay, the string, or maybe an integer or something like that, and then it's going to know where the next guy is. And so in C4 memories is the actual payload, and in C5 is a link to the next guy. And in that location, okay, so this C5 contains, oh, you should go to C0, and you go up to C0 and find, oh, there's the next guy, and at C1 I can expect the address of the third guy, and then the third guy has his payload here, and then he could have a null pointer saying, okay, that's it, that's the end of the list. And that's kind of at a high level what's going on in a link structure. So it's a little more complicated and maybe a little more convoluted. You've got this level of indirection. You've got the actual data, but you also have to have the data associated with a link to the next guy in the list. The simplest linked data structure is a linked list, and what is a little a little hard to understand at first is it's a recursive data structure. All right, we've seen recursion in methods before, so we can call a method can call itself. Well, this is actually a data type that has as one of its instance variables a instance variable of the same type that it is. Okay, this node data type, it has its payload item, but it also has its link to the next guy in the list. Okay, and the next guy in the list is also a node. All right, it's not a pointer to, it's not an object pointing, recursively to itself. It's an object of type node, all right, and a second object of type node that are connected in some way. And here is a diagram, and this is a typical way we'll draw it. Is I use a box, all right, where the left side is the payload. Okay, that's the item instance variable, and then the second box is the pointer to the next guy. And we draw it, an arrow to this guy, and this is another node object, and this is a third node object, and the second node object, its next instance variable is pointing to the third node object. Okay, and I'll usually use just a circle like this to indicate a null, and a null is normally how we terminate a linked list. Okay, we'd say it's a null terminated linked list, and we can proceed. We could start, if somebody tells us how to get to this one, then we can proceed and print out the, and then cat, and then sat. All right, and let's do an example in code. We have to create these things. So these recursive data structures, this private class node has to be instantiated just like any kind of reference type. We're going to call it first, and we're going to set its item value equal to the string the. And you can kind of think of it sort of like this: is the payload here is in memory address C4, okay, and memory address C5 currently its default value is null. So that's all we've got. Okay, we've got the first reference variable, and that gets us to these two bits of memory. The first is .item, which is the, and the second is .next, which contains the null pointer. We can then instantiate a second guy, and maybe Java puts this at memory address C0 and C1, and then we've got our string, and we've got again our default value for the next. And finally, we can create a third. Okay, and here it decides, for whatever reason, to put it at C8 and C9, and then here's the payload, and here's the next pointer. So diagrammatically, what we have is three nodes all floating in space, and there's no relationship between these three words. Okay, and now what we can do is we can hook these up. We can hook up the next instance variable of first to second, and the next instance variable of second to third, and that will create our linked list. All right, there's the first line. We assign first.next equal to second. Now we assign second.next equal to third. Okay, and now we've got a completed linked list. And if we started at the first guy, we could walk along this chain if we wanted to. Okay. Here's how to do that in code. If we want to traverse a linked list, and we assume it's null terminated. Okay, not all linked lists would necessarily be like that. For example, you could have a linked list that is circular or something. Let's loop over we'll traverse the linked list, assume it's null terminated, and then print out things in the list. And here's the code that does that. We set some local variable current equal to the start of it. So somebody keeps track of that first guy. All right, we know what the first node in the linked list is, and then we keep looping while we haven't run out of things. Okay, and we're going to detect we run out when that current variable equals null. So it's not going to start out as null because first is pointing to that very first node over here. All right, we print out that item, so current.item, this would print out the, and then here's our idiom for moving one. So it's kind of like the I++ of linked lists. Current equals current.next. What that does, right, current is currently this first guy. It's pointing to this node object. Current equals current.next assigns current equal to whatever this thing's assigned to. Well, this thing is pointing at this guy, so now current's going to point at the second node. All right, and then that second iteration of the loop is going to print cat, and then the third iteration is going to put sat. And when it's on sat, current is then going to be equal to current.next. Well, current.next is null. All right, and that's what causes the while loop to terminate. And in the bottom, you can see there you can also do that with a for loop. All right, and here's the for loop variant, which does exactly the same thing. All right, here is that code being traced out with the arrows. So we start on that line of code. All right. Current is going to be first, so what is current.item? It's the, All right, and here's our current. You can see our current guy here is pointing to that, so this is that local variable current. Then we advance it. All right, the current equals current. That next advances it there. Then it prints out cat. Then it's going to advance the sat. Then it prints out sat. And now the advance takes it to the null pointer, and then we're out of it. All right. Let's implement a stack ADT using what we learned about linked lists. All right. And how do we do pop? Well, if we have a stack ADT implemented by a linked list, what are we popping? Well, the value we're popping is the first dot item, whatever is in the item instance variable of this, and then we need to move the first pointer to the next item. All right, because this guy's gone. All right, if we say this is the the top of the stack, if we pop the top of the stack, then best is gone, and we don't need it in the linked list anymore. Okay. All right, that's moving. That's essentially what we want to achieve, right? So we want to find out that the word to pop is best, and then we want the first pointer, okay, to point there, and then that guy is just going to get is orphaned and will get garbage collected. All right, and that's because nobody's pointing to him, right? These guys are all alive as far as the Java garbage collector is concerned, because first points to this guy, and then this guy points to this guy, and this guy points to this guy, so they're all keeping each other alive. But the second we advance this first guy to here, there's nobody pointing to best, and there's no reason for anybody to be pointing to best because he's kind of been dropped. He's gone from the linked list. So how do we push something? So say we pop that, and now we want to push. Well, we need a new word. Okay, we can create, let's say we created in a variable. We went node new guy equals new node, and we set the item equal to best, and the next instance variable is equal to null. He's currently not hooked up though, so we need to hook him into the linked list. All right, we want him to point to whoever used to be on top of the stack, because now we're the top of the stack, and then we want to switch that first variable to be here. So first is always going to point to whoever's at the top of the stack. All right, and at that point we have successfully pushed a new word onto the stack. All right, so to summarize, we've had a whirlwind tour of different ways to implement our friend the stack ADT. We saw in the activity how to do it as a fixed array, and today I showed you you could grow it dynamically by using a fixed array, so just increasing it by a size of 1. Much more sensible idea is to double its size, okay, and this is really similar to what the Java array list does. And then we got our first introduction to linked lists and linked structures today, and it's a very common construct in computer science, and it takes a little while and a little practice to get used to them and learn how to to program them and debug them and so on. But they're really worth doing because you can create your own arbitrary data structures. So a list, okay, I mean, maybe you're thinking, well, I should just use the array list for this, but there are much more interesting structures. A list is just the simplest example I can show you, but there are much more interesting structures that just don't lend themselves to being represented as a linear list.